see it. So we're going to talk about just simply multiplying polynomials. Okay? It's a rather simple topic because all we have to think about is multiplication. And throughout this entire topic, what I want you to think about is the law of distribution. When you have the distributive property, right? When you distribute something to several terms, that's physically what this entire section is about. If you can distribute, you can do this. But we're going to expand upon regular distribution. So let's first start with a simple rule. You don't have to memorize this rule if you don't want to. I don't necessarily force students to know this like FOIL as the acronym. But the real law, the concept here is called double distributive. Double distributive or triple distributive. So think about a polynomial. Okay, if you have two polynomials multiplying each other as double or triple distributive. Now, there's another method some people, raise your hand if you've heard of what's called box method. Do you ever use that where you write like a little table?
I've heard of it.
So some have done that. It doesn't matter which way you want to do it. Okay, you can use it just by actually showing the arrows with distribution. You could do it all up in your head. You can use a box, whatever is reasonable. So we want to think about using the FOIL method if there's two binomials. And the only reason FOIL is useful is because it's an acronym, and people like acronyms. Acronyms are called mnemonic devices. They help trigger a memory in your head that says, oh, I know what that is actually, because of A, B, or C. Okay, that's literally what it is. It's a mnemonic that triggers something in your head to remember where it is. So, whoops, if I have two parentheses set up like this, x plus 2 and x minus 7, these are both binomials. I'm multiplying them, so I can use what's called FOIL. And if you haven't ever used FOIL before, I'll quickly show you. First means multiply the things that show up first in each binomial. That would give you x squared. Outer means multiply the things on the outside. That's x and negative 7. That's going to be negative 7x. Inner means multiply the things on the inside, which is 2 and x. So that's a positive 2x. And then last means multiply the things that show up last, which are 2 and negative 7. Which gives me negative 14. So foiling this out, that's the way it's not grammatically correct. Okay, foiling it out, we get this as a result. So that's the FOIL method. A lot of you have used double distributive, box, or FOIL at some point, I'm sure, or just regular distribution. But the concept here is this. Let me explain where this comes from. So it looks like how many operations, how many times did we multiply just now? How many times? 4 times. And the middle terms sum together, didn't they? That's always going to be the case. So that's not something you should have to worry about. If you have to multiply 4 times there, the middle terms should sum together, assuming it's set up like this.
Unless there are 3, where you go like 1, 2, 3.
Sure, if there's 3 or if there's different variables, there are exceptions. But I mean for a case of this, right? Now, why are there 4 multiplications? Here's why. This is really called double distributive. Make believe, cover up the x here. Cover up the x, okay? How would you distribute the 2? You'd multiply to both of those, wouldn't you? Cover up the 2. How would you distribute the x? Multiplying to both of those, right? That's literally what you just did, except using an acronym called FOIL. So you don't have to memorize FOIL if you don't want to. But this is really called double distributive. Those 2 get multiplied with arrows, and those 2 get multiplied with arrows. And as a result, you're multiplying 4 times, giving you 4 terms, as seen via FOIL. It's the same thing. Is that clear what I'm saying right now? So if I distribute both terms of my first binomial to both terms of the second binomial, I would get 4 terms in the end, therefore having the same answer as foiling. George?
Is there I wonder if the trinomials,
Yeah, for trinomials, there's no acronym, but you have to remember triple distributive. So see the thing I drew with the arrows? That's what we're going to do when it's a trinomial times a trinomial, or a trinomial times a binomial. Anything beyond or bigger than 2 binomials multiplying, you pretty much use the distributive rule, which is with the arrows. So if I had 3 terms, all 3 terms get distributed to all 3 terms, making it 9 answers, and then combining like terms. So box method is useful because it's visually a little bit more easy to interpret. So here's box method on the side. Draw yourself a box with as many columns and rows as terms you have in each. So since this is a binomial by a binomial, 2 by 2. If it was trinomial times binomial, it'd be 3 by 2, like a matrix, okay? So draw yourself those boxes. Simply put the actual value. So x plus 2 goes on the top. This is x, and this is positive 2. Along the side is x and a negative 7. That's the other factor. So the terms inside of your factor go as headings. Again, x, let me point to this. Remember I talked about vocabulary in this chapter? Here's where it plays a role. Ready? The terms x and 2 within this factor, the terms within this factor become your headings. The terms, these are called terms, the terms within this overall factor here, I'd rather you look up to see this, the terms within this overall factor go as headings here. This is a factor, this is a factor. These are terms inside of those factors. Okay? Terms add and subtract. Factors, what do? Multiply. Okay, that's why these overall things are called factors, because this is really a time symbol in the middle here. These are called terms because these are plus signs or minus signs in the middle.
So is that like a Punnett square?
I don't know. I'm not familiar with Punnett square. Well, do you get this? Let's see. So you just simply multiply. Do like a zipper. Multiply these two, you get x squared. Then multiply these two here, you get 2x. Then multiply the negative 7 and this x here, and you get negative 7x. And then you can do 2 times negative 7 gives you negative 14. And recognize that these four terms here are the same as these four terms here. X squared minus 7x plus 2x minus 14. X squared minus 7x plus 2x minus 14. Same terms. So when you get the answers in the box method, at the end, you just combine like terms. Questions at all? So you have three approaches. You see that? Three different approaches. You can go with FOIL if it's a binomial times a binomial. Or you can use box or double or triple or quadruple distributive if it's beyond binomials. If they're bigger than binomials, you have to use either distributive, double or triple or whatever it is, or box method. FOIL doesn't make sense to use when it's beyond this because you don't have outers and inners because now you have three terms if it's a trinomial. So this law of FOIL does not work if it's beyond 2 by 2. So this is where I tried to push a physics example, but it's not necessarily realistic. Let me explain why in the end. But just a general idea to give you a little knowledge. So in an electrical circuit, you have current. Current is the amount of electricity flowing through the circuit. It lights a light bulb or it powers some sort of a engine, whatever you're using in that case. And that's measured in amps. R is what's called the resistance. That's the material property that slows down the flow of the current, or a resistor along the way to what's called regulate the current. And that's measured by R. And then you have what's called the voltage. Voltage is the amount of volts, and that's called the potential difference, the amount of energy that's different between the two terminals of a battery. So that's all information given. And it seems like it's confusing, but I'm then giving you the law. So that's all extra stuff. Do you see that? I'm giving you units so that your units, you can see what they are. But all this stuff that I gave you up here really is extraneous. This is what's important right here. You're told that the voltage function is equal to the current, right? That was represented by current, times the resistance. I'm giving you the current. I'm giving you the resistance function. So I'm asking you to find the voltage function. Okay, so I want you to, again, determine the voltage function and then find the current, resistance, and voltage at 2 seconds. So we're going to see how we're going to apply last chapter into this problem by evaluating the function at t equals 2. Okay, like we did last chapter with compositions, f of g of x and f of 2 and g of 7. We're going to do that in this problem as well. So if I wanted to find the voltage, I would multiply current times resistance. Current, I'll highlight for you so you can see. Here's our current function right here. We'll take that and multiply it by the resistance function right there. So go ahead and practice this. Pick which way you want to use. Use either triple distributive or box. Triple distributive or box. Either one works. And remember, this is equal to the voltage function because the voltage function is defined over here as current times resistance. So I'm just showing the setup right now, okay? Current times resistance. Whichever way you want to choose to multiply, you can choose. I'm going to use triple distributive. If you're using triple distributive, that should be your first step. Take that first term, distribute it to all things in the next. Check your answers, please. You should know your laws of exponents, the ones that we went over at least. Okay, that was from section 4.1 and 4.2, your laws of exponents. So you got to know that when you're multiplying things that have the same base, right, the base is t for both of these, you have to add the exponents. The 2 gets multiplied by this coefficient, which is a 1, still remaining as 2, t to the 6th. And then I would go through the next 3. Make sure you carry over negative signs when applicable.
Will there be physics problems like this on this?
I mean, I could give you a problem like this and you should be able to do it. I mean, it really isn't any more difficult than any problem we've done because I'm giving you a formula and I'm giving you the functions. So it definitely could. This could be like a word problem, but I'm really forcing it here, okay? This is really like me trying to just introduce some sort of problem solving because there's no application of this problem solving until you get to physics or science. Where was that? 4t to the 4th. And then I have... Okay. So again, check your answers with mine as you're going through. Even if you're doing box method, you should get the same answers. Inside your boxes, you should be getting these numbers or these expressions that you're seeing here. And then finally, the last part, please notice, you need to distribute -6. It's a -6, which is going to make this negative, and this positive. Distribute -6 in the end. It's really long. You're going to have 9 terms. You know you have 9 terms because it's 3 by 3, right? They're each trinomials. Okay, check your answer, see if you got that, and then simplify. Okay, collect your terms. Just look for all of your like terms and do it in decreasing order of degree, please. So starting with 2t to the 6th, there's nothing else to the 6th. There's only one thing to the 5th, so that goes by itself also. Then I go to the 4th. Oh, there's only one thing to the 4th also. Jeez, that's annoying. All right. So far I've got my 6th power, my 5th power, my 4th power accounted for. This is how you know you didn't forget anything, right? Go in order. It makes sense. Once I get to the 3rd power, I've got -10 plus 8 minus 6. -10 and -6 is -16. -16 and +8 is -8. So this is going to be -8t to the 3rd. Please recognize that when you combine like terms, you're just simply adding the coefficients. That's all you're doing. Okay, and then finally we go to squared. That's going to be -12t squared. And then linear term, is it just one linear term? Yeah, -20t plus 30. Is that correct? Did I do everything right? Did you get the same answer? I'm seeing nodding. There was only one thing that was a like term, and I'll circle it so you can see. And it's to the 3rd power. Only one degree. Those were the only like terms in this entire problem. Everything else did not have a companion term that you could like compare, or the same term you can combine it with. How many people use box method out of curiosity? It doesn't matter. Either way, I just want to know, actually. I really do. Please be honest. Raise your hand. Use box?
Yeah.
Did everybody else use the distributive like that? You all did it the other way? Okay. Yeah, every year it's different, honestly. Sometimes it's half and half. Sometimes you do it for some problems, others for other. Okay. Last part of this problem here says determine everything after 2 seconds. So how do you find let's start with the current after 2 seconds. What's the current after 2 seconds have elapsed? How do you find that? What does that mean? Yeah, so we need to use the current function at 2 seconds. So what's I of 2 in this case? I got to plug it into the I function, right? Plug it into the IT function, plug in the 2. What do you end up getting? 18. So to see that, I have 2 times t cubed plus 4 times t minus 6. Where am I getting all of this from? I'm getting it from up here. Here's the current function right here. So I'm looking at the current after 2 seconds have elapsed. So 2 goes here, and a 2 goes here in those spots. 18, yes? The resistance Resistance.
11.
11. Is Ash the only one that got these? Anyone else do these yet? I'll give you a minute to do them. So we're just plugging in the resistance function here. And again, we're plugging in 2. It's going to be 8 plus 8, 16 minus 5 is 11. Now, check those numbers first. Okay? For the last part, I have 2 ways to approach. The last part says, determine the voltage after 2 seconds. Why are there 2 ways to approach this problem? What is voltage defined as earlier in the problem? Look up at the top. What is voltage defined as? The definition of voltage is what times what? What do you got, Hannah? The current times the resistance. So I can take 18 times 11 and just get my answer. Does everybody see that? Just 18 times 11, there's your answer. Or what could you do? What else could you do? What's the second opportunity? You're trying to find the voltage. Here's your voltage function right here. After 2 seconds, what can you do, Bridge? You can plug in 2 into that. So remember that this, I didn't write it, I should write equals V of t, is the voltage function. This was our answer from the first part of this problem. So you can plug a 2 into that. But honestly, if you're taking a test, it is so much longer plugging a 2 in here than it is about just doing 18 times 11. You're done. Does everybody see what I'm saying here? Again, you can take the voltage function, plug a 2 in, that will take you about, 30 seconds to a minute. Or you can do 18 times 11, which will take you 5 keystrokes or a little bit of brain power. Either one, right? Either one. So what do we end up getting? Voltage 198? 198?
Yeah.
Okay, volts. If I put units, these were amps and these were measured in what were called ohms. Okay, the units are not as important as the answers were for now. When you get to physics, the units are extremely important. You'll see that, but I'm not going to hound on them right now. Okay, but these were the units. Amps, ohms, and volts. But don't focus on that. Focus on the approach. Questions so far? Okay, we're doing all right on time. So example 2 asks us the following. If we're given some functions and we want to figure out products of those functions, how can we express them? So let's start with part A. So we're given h of x, g of x, and u of x. And part A says, what is 2 times g of x times u of x? What is 2 times g of x times u of x? So what approach might you take? There's 2 ways to approach this. What do you got?
Well, you could plug in g of x, and then multiply it by 2, and then put in that, and then when you distribute the 2 first, and then you multiply the 2.
Yeah, so Tristan's saying you can double all the coefficients in g of x, and then multiply that answer by u of x. Or you could do what else? Multiplication is commutative. What else can I do? It's also associative.
You just do gx multiply ux first, and then you use 2 to multiply the whole thing.
Same thing, right? So same approach. Doesn't matter whichever way you want to do it. Go ahead and practice, please. Just take g of x times u of x. You have your functions that are given for you. Either multiply first, then double, or double one of those things and then multiply. But please, do not distribute the 2. That's the common mistake here. I've seen students distribute this 2 to both functions. Either double g and then take that answer and multiply it, or multiply these and then double the answer. But do not distribute a 2 in this case, meaning this 2 right here does not get distributed. Anybody got an answer yet? Getting there? What do you got, Luke?
and negative 12x cubed plus 10x squared minus 4.
Anybody else got this?
I got negative 24x cubed plus 20x squared minus 8.
Yeah.
What did Luke forget to do? Luke, you did the whole thing. We got to double it, right? Good. So g of x times u of x is indeed this, and then you need to double all those coefficients. Be careful. That's the common mistakes on the test, right? We always talk about that. Careless, guys. Make sure to read the problem carefully. Part B, I want you to do, but please, before you do part B, also look at part C and think ahead. Okay, think about how you're going to use part B for part C. Practice part B. That shouldn't be that bad. It's just a binomial, so part B, if you want to FOIL, you can FOIL or box method or double distributive for part B. But then please utilize that in part C. Don't do part C from scratch. So part B, I'm going to put the answer up so we can see. So this was part A right here. Part B wound up getting 8x squared minus 8x minus 6. So when you go to do part C, what was I pointing out? Anybody recognize yet? Why was I saying, making a big deal about using part B? Max, what do you got?
You just plug in 8x squared, that function, or 8x squared minus 8x minus 6 multiplied by 4x plus 2.
Multiplied by, careful?
Oh, sorry, g of x.
Yeah, good. Very good. So g of x is really just multiplying times u of x and h of x here, right? So take your answer from part B and just multiply it by g of x. You've already got h of x times u of x from part B, and that shows up in part C. So what I'm saying is rearrange part C and write it like this. And then recognize that this was already solved for, you already solved for h of x times u of x in part B. Take that answer, multiply by g of x. For the sake of time, I'm going to press on to the next one. I know a lot of you are still writing furiously, and that's good. Sorry, I want to press on, though, just because of time. And I really get to these last two cases here. Maybe I'll let you go back and then finish it, or if you want to finish it, you can just continue. So these are special cases that we've really seen abundantly in math and science in general. They show up a lot, a real lot, to the point where it's actually worth memorizing some things. Okay, normally I would not say to memorize something if it doesn't really show up a lot. So for example, the quadratic formula, if you haven't learned about it in your last school, is something you will memorize this year because it shows up all the time. It's in so many different types of problems that it is necessary that you really do memorize it because you use it so often in math and science, you don't want to look it up all the time. Same thing happens here. So let's start with case 2. I think case 2 is the one that students see most often. Okay, so let's start down here at the bottom, actually. And I think you've probably seen this already. And this is actually called difference of two squares, or two perfect squares. But instead of factoring, which we're going to do, we're going to factor. Right now, I'm showing the multiplication that gives the answer. So remember that if you have something that looks like this, you can factor it into this, right? Just like, look over here. A lot of you have learned that this factors into this. And you see that these are both squares and that there's a difference here, which is why it's called difference of two squares. The answer turns out to be a difference of two squares. Why is this happening? When I multiply these out, x plus 4 times x minus 4. FOIL it out for me. What does it actually, give me all the terms. What does it become, George?
It becomes x squared minus 4x.
Yep, good. Same thing. The same thing. I did it backwards. Keep going.
Minus 16.
And what happens, George?
Cancels.
Yeah, the middle terms will always cancel out. I wrote them backwards. It doesn't matter the order because I'm literally knowing what they're both going to be. They both always cancel. That will always happen. Whenever your two things that you're multiplying are binomial conjugates. Write down the word, please. This is another term. These right here, put a little arrow coming from both of them. They are binomial conjugates of one another. Binomial conjugates of one another. You can't just have a binomial conjugate. You have to have both. So if you have a minus c, then a plus c is its binomial conjugate. If you have 2 plus 5, which we all know is 7, right? I get that. But 2 plus 5 and 2 minus 5 are actually binomial conjugates. Kind of weird, right? Because you would simplify them, so you wouldn't really do that. But 2 minus x, what's its binomial conjugate? 2 minus x, and then 2 plus x. It's just switching the sign in the middle. Whenever you multiply binomial conjugates, the middle terms will cancel. Is that clear for this part? Again, when you multiply binomial conjugates, as seen here, the middle terms will always cancel, yielding a solution that will always have difference of squares. These are all squares. Look at them. They're all squares. 9/4, right? That should say k squared. Typo. Make a squared symbol here, please. Add that little squared symbol in your notes. I got to fix that in the notes. 9/4 k squared minus 4j to the 6th. Those are both perfect squares. How about the first case? What's the whole idea with the general rule for the first one? What's happening there? Start with an easy example. I put an example that's a little difficult to start with. Start with this. X plus 2, quantity squared. You know what I see all the time? X squared plus 4. And they distribute the square to both of those. You can't distribute the square. You can only distribute a power when there's a product in the inside of the parentheses. If that was x times 2 in the middle to the second, then you can distribute the square to both. But you cannot distribute the square. What do you have to do here?
Wouldn't it just be, you just have to x plus 2 and then another x plus 2?
Exactly. And keep going, Bridge. Keep going.
So
what does that become?
Boil that out, so it would be x squared plus 2x plus 2x, so it's, I guess 4x, and then plus 4. So the final thing would be x squared plus 4x plus 4.
Very good, Bridge. And what I want you to pick up on is this. You can follow a rule if you'd like to. I don't personally memorize this rule, but it's very useful when you're factoring. Here's what you'll notice. The n terms out here are always what your first terms were squared, right? So look at this over here. See this number here? It's really just this squared. See this quantity over here? It's really just that number squared. That's all it is. In the middle is double the product of both of your terms. See 2ab in the rule here? It's double the product of these terms. So what's the product of 2x and 5y? 10xy. Double that. 20xy. That's always going to be the middle term. This will be useful when we're factoring, really. When you're multiplying out, I personally wouldn't even memorize this rule. Okay? But we're going to factor and we're going to do the reverse, and then it's useful. Homework, please. Make sure you get to your homework.